Hello friends, let's design layout for 2 input NAND logic. Before actually going to the layout designing, let us briefly first understand the circuit design using the MOSFETs. So there are total 4 MOSFETs, as it says CMOS technology, complementary pairs are there, 2 PMOS and 2 NMOS. So 2 P MOSFETs which are connected in such a manner the source of both the MOSFETs are connected together and is provided with the VDD, and these two MOSFETs are P MOSFETs. Then drain are commonly connected with each other and it is connected to the drain terminal of the first N MOSFET. So common drain output is taken here. Then this is second N MOSFET. So the source and drain of these two N MOSFETs are interconnected with each other, and the input A is applied commonly to the second transistor. Let us call this as a pair of transistors, so where both of them are provided with input A and these two transistors are provided with input B. The structurally same circuit can be drawn in different way. In different books it is given in different way. But how it works is, it follows this particular truth table. So this is the truth table for NAND gate. Even if a single input is 0, then output leads to VDD. How it happens? The is actually observing the MOSFETs, these are as if connected in parallel connection. So if either of the transistors starts, then VDD flows through the transistor. Ideally it acts like a short circuit. Practically it will take some small voltage drop across itself, and through these transistors VDD will try to appear at the output. So this is equivalent to the logic 1 state. So if either of the two transistor works, so when the P MOSFET turns on, we know that if it receives the input as a 0, because 0 minus VDD, it is equivalent to the minus VDD voltage. And to make the PMOS on, its threshold voltage, which is negative voltage, so its value should be negative. Suppose if it has a threshold voltage of 2 volts, so minus 2 volt, gate to source voltage is sufficient. But if we provide here the 0 input, 0 minus, suppose VDD is 5, 0 minus 5 leads to minus 5. So minus 5 is more than sufficient to make the transistor in fully on state. And that's why, for if any of the input is 0, then output leads to VDD condition. What will happen if both the inputs are VDD or logic 1 state? So PMOS, both the PMOS will be behaving like a open switch. It will not turn on, because if you apply here the 5 volts, 5 minus 5, it leads to 0. So for 0 gate to source voltage, PMOS will never turn on. So both of them behave like a open switch. So there is no concern of VDD appearing at the output. Now let us see what happens with N MOSFETs. So when this is received with high voltage logic 1 state, and N MOSFET, this is also received with logic high state. So the ground logic 0 state may appear at the output if and only both the transistors are in on state. So to make both the transistor in on state, the only condition is both the inputs should be provided with voltage VDD. So this is the circuit diagram and this is the truth table. Now let us go and design the layout using the Microwind software. Make it clear how the connections are done. So for the convenience, I have labeled these terminals also. Source, gate, drain for P MOSFETs, which are labeled with 1. Let us call this a transistor 1, transistor 2. M indicates these are the MOSFETs. P MOSFET with input B, P MOSFET with input A. Accordingly, these are the pairs, complementary pairs of P and N respectively. Make a note, both the source of P MOSFETs are connected together and they are provided with VDD supply. Drains are connected together from where the output is taken, and from the same terminal, one of the drain terminal of one of the N MOSFET is connected. So in this way, we'll be designing the layout in Microwind. Okay, now let us continue and design here. Now we require initially the 2 P MOSFETs. So from the palettes, I will select the MOSFETs. So MOS generator. So initially I will choose the P MOSFETs. I need the 2 MOSFETs, so I will make this as a 2. I will keep the settings of width and length. By default, whatever it is, I will keep it as it is. And just set the generator device and click on the screen. It will generate the two P MOSFETs. So if you click here, the layout will be observed on the screen. Now I will stretch and move this so that it fits onto the screen properly. Now these are the two P MOSFETs. Let us go for two N MOSFETs now. Two N MOSFETs again with the same width and length. Generate a device. It will generate a device with two N MOSFETs. So click onto the downside of the screen. Otherwise, if it is too much adjacent, it becomes difficult to separate out. Again click onto the stretch and move icon and bring it exactly onto the downside. So we can make the connections and the layer joining of the layers easily. So these are the two P MOSFETs, these are the two N MOSFETs. See, always P MOSFET is itself designed with N well, but this N well should be provided with VDD so as to work it properly. So I will add here the VDD. So along with that we have seen, so if these are the two P MOSFETs, I will call this as a source, gate and drain. Source, gate and again drain. Or we can call interchangingly, we can give labels to these terminals as well as per our convenience. So right now I will call this as a source, this as a gate and this as a drain for the first transistor. And this is again drain, this is a gate and this is a source. So already we have seen source of both the transistors are connected together and they are provided with VDD. So it's moving down. I will shift it to lower section slightly. Okay, this is okay, fine. Now I will select the metal one and extend the layers of both the sources so that we can interconnect both of them. So the source of both the P MOSFETs, it will be interconnected with each other and provided with VDD supply. So these are provided with VDD supply. This is VDD. We have seen source of both the P MOSFETs are connected with VDD. So this is VDD. Then what next? We can give the proper labels also here. So I will call, or we can give it that at the end. We close this. Now next is, what about both the source of N MOSFETs are grounded together. So we'll extend this layer again. Same metal, I will choose the same layer. Extend this layer for both the sources. And then I will join these two layers. Okay. So here what is to be connected? Source of both the NMOS are connected to the ground connection. Fine. Now what next? So I will call this as a source, gate, drain. Again drain, gate and source. See, these two terminals are interchangeable, source and drain. As per the convenience of layout designing, in this case we can interchange the terminals. Means if you assume this as a source, gate, drain, we need not again assume the same sequence, source, gate, drain. We can consider this as a drain. So from common drain terminals we take the output. So I will again extend this layer to the down side till this point. Now see, this is a source. I think I have done something wrong. We should delete this part. Go to the edit, or we can delete some layout. Actually this is not commonly connected, only this much part is connected. Fine. So actually only source of one NMOS is connected to the VSS again. Okay, so this should be ground connection. So this is the ground connection. Place it here, because only source of an NMOS is connected to ground. And this is the drain, gate, source. And again this is a drain, gate and source. So I will extend this drain part and join it here. Now I will take the common output from these 2 points where I can take the output. Here we can place the output. Now next part is we need to join the polysilicon layers. So I will join the 2 polysilicon layers so as to provide the input. So these are the gate terminals of both the transistors, which is to be provided with the clock pulses. So I will apply the clock pulse to first one. I will call this as the input A, assign it with this much time period. Similarly, we should assign this clock pulse to the second input gate. So I will call this as the B and then assign. So by default, visible in simulation is enabled. If you press this, then this particular level will not be observed. By default, it is visible in simulation. So just click onto the assign option. Now we want to check the output also. We'll check here the output. So I will change the label as a V out. Okay. So we need to check the design rules, design rule checker. Use the design rule checker. Let us see. Yes, no error is there and 0.8% memory is used, so we can simulate the circuit successfully now. So these are the waveforms. So what the waveform says is, see, this is the input A, input B. So what the NAND gate says, for both the inputs 0 only, which single input is 0, output should be 1. So this is 0, output is 1. When both the inputs are 1, then only output is 0. So 0, this input is also 0. 0, 0, output 1. 1, 0, output 1. So it has considered all the 4 conditions. And that's why the frequency of in clock A and clock B, it should be different. Either it can be half of each other or the double. Either will work. So that all the 4 combinations will be covered. Now same thing can be tested by connecting one capacitor. So you can click here, you will be observed with the palette connection. Now if I connect one virtual capacitor to the output terminal, which will behave like a load, and wherein we can check how the variations are there in the rise time and fall time. So let it be 0.01 picofarad. Click OK. Again simulate the circuit. See, these are the variations. So where it is switching from 1 state to 0 state. So it is taking a long time. Almost complete cycle it is taking for the fall time to come to the original value. Again rise time, this is, it has affected. So this is effect of connecting the capacitor as a load. So now along with this, for the convenience, we can give proper labels also. How we can give the labels is, if you click here A, this is the add text to the layout. So I can give the labels here. So this is the source terminal for the first transistor. This is the gate terminal. And accordingly, this is the drain terminal. So we can call this as a drain terminal. So this becomes source, gate and drain for the first transistor. So for the second transistor accordingly, this is the common drain terminal. So we can call this also as a, we can give this label as a drain terminal. This is again gate for the next transistor, and this I will call it as a source terminal where it is grounded. So I will call this as a source. So this is for source, gate, drain for first PMOS. This is again for the second PMOS, which are connected. Similarly, we can give the labels here. We can give the labels. You will understand. It's a common drain output terminal. So we can call this as a drain terminal. This is the source terminal. And this is again same with the drain terminal. So sorry. This is also the drain terminal for next transistor, and these are the gates. So this will be obviously source terminal. Okay, that's it.